Welcome to this NPTEL lectures on robotics. In the last lecture, I had shown you examples of equations of motion of a planar 2 degree of freedom robot and a planar 4-bar mechanism derived using the Lagrangian formulation. In this lecture, we'll look at what to do with these equations of motion. Specifically, we'll look at two problems in dynamics. One is called inverse dynamics and one is called direct dynamics. And the direct dynamics problem involves simulations of equations of motion. Okay, so let's continue. So as I said, there are two problems in dynamics of robots. One is inverse dynamics, which is given dh and inertial parameters and a trajectory as a function of time. Find joint torques. Okay, so we need to obtain tau of t from known q of t, q dot of t, and q double dot of t. So q of t is the trajectory as a function of time, and q dot is its first derivative and q double dot is the second derivative. The direct problem, on the other hand, is given the kinematic and inertial parameters and the joint torques as a function of time, find the trajectory of the manipulator. So basically, we need to obtain q of t from known tau of t. So the inverse problem is required for sizing of actuators and model-based control. Okay, sizing of actuator means that suppose you want to design a robot and the robot is supposed to perform a set of tasks. Basically, we have an idea of q of t, q dot of t, and q double dot of t. We can solve the inverse problem. We can substitute q, t, q dot t, and q double dot of t into the equations of motion and obtain tau of t torques. And based on the maximum torques from this computation, we can decide what motors and what should be the torque characteristics of the motor. Okay, it is also used in model-based control, which we will see later. The direct problem requires simulation, meaning what? That we are given tau of t and we know that the equations of motion are second order ODEs. So we need to integrate these equations of motion to obtain q of t. So this is also called simulation. Inverse problem is very simple. Okay, why? Because all it requires is that substitute the given q of t, q dot of t, and q double dot of t in the right hand side of the equations of motion. The equation of motion is given in general as tau equals m into q double dot plus one Coriolis centripetal term plus one gravity term and maybe a friction term if there is an estimate of friction. So if you know q, q dot, and q double dot, you can just directly substitute and obtain the left hand side, which is torque, okay, as a function of time. Okay, so it can be done for any robot since the equations of motion are known. You can do it very efficiently because we will see later that this can be obtained in O(n) steps using what are called as recursive algorithms. Planar 2R example. So again, we go back to our very familiar simple example of a 2 degree of freedom planar robot with two rotary joints. Again, the mass, length, location of the CG, and the inertia are given. The gravity is acting downwards. The location of the CG of the second link is given. So there is a tau 1 which is acting on the first joint and tau 2 which is acting at the second joint. So in order to compute tau 1 and tau 2, we need to actually first assume some mass, length, inertia, and location of the CG. So in this numerical example, we have assumed that the lengths are 1 meter, the mass is some 12.5 kg approximately. CG is located 0.773 meters away in the first link and 0.583 in the second link. And the inertia is 1.042 kg meter square. Okay, so these numbers are from data from an experiment. Okay, so you might think that why have we chosen all these funny looking numbers? These are actually from some experiment and literature. So the mass inertia geometry are as in table. we now need to choose a trajectory. Okay, so in this numerical example, I have chosen a circular trajectory. So the tip of this robot should trace a circle, which is given by x is a r cos phi, y is b r sin phi. So phi is the parameter for this circle. We choose r as some point 2, a as 1.2, b as 1.2. It is located at a distance from the origin, and the whole circle lies inside the workspace. Okay, so we have this parameter phi, which varies from 0 to 2 pi in about 10 seconds. Okay, so later on I will show you the video of this, but as you can see, this is the example that we are interested in. So to continue, first we compute theta 1 and theta 2 for that circular trajectory. So we can see that the angle theta 1 and theta 2 can be obtained using inverse kinematics. So it goes, the y-axis is in radians and the x-axis is in time. So we go from 0 to 10 seconds, we go 0 to 2 pi. So theta 1 plot and theta 2 plot can be obtained. We can also compute theta 1 dot and theta 2 dot using inverse Jacobian. For the 2R manipulator, the Jacobian is simple, a 2 by 2 matrix. We can invert the Jacobian and we can find theta 1 dot and theta 2 dot. Okay, so the plot of theta 1 dot and theta 2 dot are in blue and green in these two figures. We can also find the acceleration, okay, because we have an expression which is theta double dot is some j inverse something and so on. So we can find theta double dot and theta 2 double dot. Once we have all this theta dot and theta double dot, we can just substitute in the equations of motion and plot tau 1 and tau 2. So as you can see, tau 1 looks like this. It is much larger. Okay, so it's of the order of 120 or 130 radians per Newton meter, whereas tau 2 is much smaller. So this is a simple problem. As I showed you as an example, it can be very easily done. There is nothing much to it. We just do substitution. The simulation on the other hand of the equations of motion is more interesting and a little bit more challenging. So what is the problem in simulation? You are given the external torques and forces and you need to obtain the motion of a robot. So the general equation of motion of an n degree of freedom robot can be given as tau mq double dot cqq dot, gravity term and friction term. So in simulation, you are given the left hand side and we have to solve for q of 2. Basically, we have to solve this ordinary differential equations. So these are n coupled nonlinear ordinary second order differential equations. Second order because there is q double dot. Okay, we cannot solve these things analytically except probably some very trivial simple case. Okay, remember this is nonlinear. It has sine theta, cos theta, then theta 1 dot square, theta 2 dot square, all kinds of nonlinearities are there. So we need to resort to numerical solution. Okay, so we go to MATLAB. Okay, we use a software tool such as MATLAB, which has inbuilt integration routines. Okay, so for example, if you go and look in MATLAB, there is something called ODE 45. Okay, ODE 45 means some fourth order, it's a predictor corrector method, fourth order predict and fifth order correct. Okay, Runge-Kutta based methods. So the input to this ODE 45 in MATLAB requires you to give the equation in state space form. Okay, so what is a state space form? State space form basically means should be of the form x dot equals to g of x comma tau. Okay, we need only first order ODEs. So I need to convert my equations of motion, which are second order ODEs, to first order ODEs. So it is possible and it is not very hard. So what we first do is we rewrite the equation of motion by using the inverse of the mass matrix. The mass matrix is always invertible. Remember, it's positive, definite, symmetric. So Q double dot can be written as M inverse tau minus C minus G minus F. Okay. Then we define a state vector X, which is X1 through Xn, which are nothing but Q1 through Qn. Okay. And Xn1 plus X2n, which are nothing but X dot Q1 dot to Qn dot. Okay, so basically we have n second order equations. We can rewrite it as n first order ODEs. Okay, so x1 dot you can see is nothing but xn plus 1. Okay, x1 dot is q1 dot, which is xn plus 1, and likewise x2 dot is xn plus 2, and so on. So what do we have? We have xn plus 1 dot all the way to x2n dot, which are nothing but q double dots, is m inverse tau minus g minus f. So we can substitute q and q dot as x in this, and we can get this equation. So what are the equations that we have? We have x1 dot is xn plus 1, x2 dot is xn plus 2, and so on. And xn plus 1 dot is given, and xn 2n dot is given by this. So combining these n equations and another n equations, we get 2n first order equations, which can be written in the form x dot g of x comma tau. Okay, so remember, xn contains q's and also q dots. It is a 2n variables. Okay. So in order to solve this first order ODEs, we also need initial conditions. So basically we must be given what is q and q dot 0 at time t equal to 0, which is x at time t equal to 0. So for parallel manipulators, we can rewrite the equation of motion again as mq double dot, which is f minus some psi transpose, then psi m inverse psi transpose, and so on, where psi is the constraint matrix and f denotes tau minus c minus g minus f. So we are dropping this, that it is a function of q's or x's. So in parallel manipulators, we can get 2 into n plus m first order equations. Again, x1 dot is xn plus m plus 1, x2 dot is this, xn plus m dot is x2 into n plus m, and xn plus m plus 1 dot is m inverse something. So the x2n dot n plus m dot is m inverse f minus psi transpose this matrix into psi m inverse f plus psi dot. Okay, so again f gives you tau minus c minus g minus f. This is what f denotes, where tau is given. Okay, so again we can rewrite this equation as x dot is equal to g of x comma tau, where now the x is 2n plus m variables. So we have 2n plus m first order equations for parallel manipulators. Okay, so the nature of ODEs in a parallel manipulator, they look similar, but they are slightly different than the ODEs obtained for the serial manipulator. Okay, let's discuss this a little bit. So the m loop closure equations must be satisfied at all instants of time. Okay, so not only do we have differential equations, but we have m loop closure equations, which are holonomic constraints. They do not include time. Okay, they don't have derivatives of the variables of the passive joint variables. Okay, or the actuated joint variables. So this set of some differential equations and some holonomic constraint equations are also called differential algebraic equations, or DAEs. Okay, the DAEs are inherently stiff. Okay, so what do we mean by stiff? A system of ODEs is said to be stiff if the time constant of the individual ODEs are orders of magnitude different. So more than, let's say, 10,000 is to 1. Okay, what do we mean by time constant? We have x dot is equal to g of x comma torque. Okay, so this is essentially given an input, the x will take some time to reach the state. Okay, similar to later on we'll see what happens in control. So there is something called time constant for any differential equation. Now, if the time constants for some variables are much faster, or the time constants are much slower, smaller than the others, then these equations are called stiff. So there should be a spread in time constants, and if it is more than 1000:1, we call them stiff. So for stiff ODEs, the time step in integration is determined by the smallest time constant, and hence a set of stiff ODEs can take very long to integrate. So we have to take very small steps if the time constant of some equations are very different than the other. So DAEs can be thought of as infinitely stiff, since the algebraic constants have zero time constant. Okay, so there are these algebraic constraints, polynomial constraints, they have zero time constant. So DAEs are inherently stiff, but it's not so serious because we can use stiff solvers such as ODE15S or ODE23S. So S stands for stiff solvers. Okay, so stiff solvers use what are called as implicit schemes. Okay, they are not marching forward in time. They solve a set of equation at each time steps. Okay, and are inherently slower than non-stiff solvers. However, for simple problems such as 4-bar mechanism, ODE45 is good enough. So we can use ODE45 to solve for the 4-bar parallel mechanism. 4-bar mechanism. Okay, so parallel manipulator, let's continue. The equations of motion involve second derivative of the M constraint equation. This is another aspect. So if you have small numerical errors in acceleration due to integration, it results in increasing errors in Q dot and Q, because the Q double dot is slightly wrong, very slightly wrong due to the integration. So then integral of that, which is nothing but summation, okay, will be more, the error will be more, and Q will be even worse. So as a result, in parallel manipulator, the Q and Q dot will slowly diverge from the real solution. So there are various approaches to stabilize this increasing errors. Okay, so one such is called as the Baumgarte stabilization. So basically, instead of using psi q q double dot plus psi dot q q dot plus phi dot q equal to 0, this is my second derivative of the constraint equation. We replace it by psi q double dot plus psi dot q dot plus phi of t plus 2 alpha into phi of t plus psi q q dot plus beta square eta of qt. Okay, so where alpha and beta are constants. So basically what it looks like is, it is like a spring mass damper system. So this is like mx double dot plus cx dot plus kx equal to 0. Okay, so if you choose properly alpha and beta, both eta of t and eta dot of t, okay, eta q of t, its first derivative, both will go to 0. Okay, just like a spring mass damper, if you choose the damping and the spring properly, the oscillations will die down. Okay, so hence, if you use this Baumgarte stabilization, where we have chosen somehow alpha and beta, then eta will be satisfied, eta dot will also be satisfied, and eta double dot is of course satisfied, because if these two are satisfied. Okay, so similar to a spring mass damper system, exactly. But there is a problem. We do not know how to choose alpha and beta. Okay. In a spring mass damper system, just to go back, we have x double dot plus 2 psi omega n x dot plus omega n square x. So beta is similar to the natural frequency omega, and alpha is similar to the product of natural frequency and damping. Okay, but this is not exactly same because it is very complicated. So we do not know how to choose alpha and beta. But nevertheless, Baumgarte showed that this kind of stabilization can work, and we can make sure that the constraint equations are satisfied at each instant of time. So let's take some examples of simulation. So we have a planar 2 degree of freedom robot. Again, we have these two links. There is a tau1 and tau2. There's a gravity vector which is acting down along the negative y-axis. And we have M1, L1, R1, and I1. For link 2, you have M2, L2, R2, and I2. So we take the same lengths and inertia which was done for the inverse dynamics similar problem. So length is 1 meter, mass is 12.456 kg, and so on. Okay. So the initial conditions are theta 1 is 90 degrees, theta 2 is 45 degrees, theta 1 dot is 0, and theta 2 dot is 0. Okay. So what does it look like? It is like a 2 degree of freedom robot which is hanging down below. Okay, so it is hanging down below. Okay, with minus 90, but the second link is displaced by 45 degrees, okay, in the vertical direction, plus 45 degrees. Okay, and then let's assume that the tau1 and tau2 are 0. So what is it? It is like a double pendulum. So those of you who have done any course in dynamics, you know what is a single pendulum, which is one link with a bob at the end, but you can also have two links connected at the joint, and this is called as a double pendulum. So this planar 2R with tau1 and tau2 equal to 0 is nothing but a double pendulum. So we can solve the equations of motion for this planar 2R robot. Okay, and we can plot theta 1 and theta 2 as a function of time. As I said, we do it for 10 seconds. So you can see the plot looks quite interesting. Okay, even the theta 2 is interesting. It is not exactly at the same frequency. Okay, we can also plot x and y as a function of time, and we can see that the tip of this robot, which is starting from here, it will go down, come up, and it does all kinds of strange motions. Okay, so what is the first important thing? That the motion of link 2 causes a motion of link 1. Okay, so remember, the first link is hanging vertically down and the second link is displaced by 45 degrees, and there are no torques which are acting on this link. So intuitively one might think that only the second link will oscillate, but that is not true. The motion of the second link causes the motion of the first link, and the path traced by the tip is quite complicated. Let's look the example of the 4-bar mechanism. So we will start with the 4-bar mechanism, which is almost completely folded. Okay, so this comes from one of these problems which we had done earlier, where a mechanism is initially folded and then you actuate one of the joints and then you see how long it takes to unfold, okay, or to deploy. So this is L1, L2, L0, and L3. This is a 4-bar mechanism. There's a torque which is acting. And since it is almost folded configuration, this theta 1 and phi 1 are very small. Okay. This theta 1 is actuated by a spring. There is actually no motor, but there is a spring. Okay. And the right-hand side of the equation, which is the torque 1 corresponding to theta 1, is given by some tau 0 minus k theta 1. So basically what is happening is there is a pre-torque or a initial torque which is tau 0, which is 1.96 Newton meter. K was chosen as 0.1 Newton meter per radian. And as the mechanism, as theta 1 increases, the torque which the spring applies is reducing. Okay. So I want to see what happens when you have this 4-bar mechanism and you apply this torque from the spring. So what you can see is, in the way these links are drawn, after a while the second and the third link will become straight. Okay, they will become aligned, and then this theta 1 cannot increase anymore. So this is called as the diploid configuration. Okay, the link lengths are chosen such that it will not rotate fully. Theta 1 will not rotate fully. So what are some of the questions that we can ask? Okay, we can first, let's look at what are some of the dimensions and mass and inertia properties of the link. So this is chosen in this form, 1.241, CG is at 1.2, and so on. Inertia is, first link is very large, the others are very small. So as the spring unwinds, link 1 rotates counterclockwise, as I showed you. Link lengths are chosen such that theta 1 cannot rotate beyond a certain angle. Okay, so link 2 and 3 locks when they align, and 4-bar becomes a structure. So after some angle, link 2 and 3 are parallel, and there is a mechanism which will lock that joint. So we initially start with some very small angle, theta 1 0.01 radians. Okay, phi 1 is this, obtained from the solution of the 4-bar kinematics. And we choose some initial value of phi 1. Okay, so we cannot start with 0 and 0 because that is a singular configuration and the integration will not start. Okay, so what are some of the questions that we can ask? I want to know at what angle it locks, number one, and more importantly, how much time it takes to lock for given mass, length, geometry, spring constant, and everything. So we can simulate this 4-bar mechanism. We can plot theta 1, phi 1, and phi 2. So theta 1 is this dark line, phi 2 is this other line which starts from and this is phi 1. Okay. So what you can see is around 150.4 degrees links 2 and 3 align. So this is a singular configuration. For this, we don't need to solve the equations of motion. We can just do geometry. You can draw the triangle and measure the angle. So at t equals 12.25 seconds, theta 1 is 150 degrees. Okay, and the simulation is stopped. Why? At t equals 12.25, you can see that the Lagrange multipliers are going off to infinity. Okay. So remember, in a 4-bar mechanism, we introduce this Lagrange multipliers for the loop closure constraints, and then we solve for the Lagrange multipliers, and then we substitute back in the equations of motion, and then solve for the equations of motion numerically. So if the Lagrange multipliers are going off to infinity, there is nothing much we can do. So, and it turns out that this is around 12.25 seconds is when the two links, link 2 and link 3 are becoming aligned and it locks. Okay, so later on I will show you this 4-bar forward dynamics simulation movie. So in summary, after the equations of motions are obtained, one can solve two problems in manipulator dynamics. First is inverse dynamics, which is given the trajectory as a function of time, find joint torques. Then we have forward dynamics or direct dynamics, given the joint torques, find the trajectory of the manipulator in time. Inverse dynamics is straightforward. It just requires substitution of q, q dot, q double dot in the equations of motion. Forward dynamics involves numerical integration, and I have shown you examples of a 2-bar planar manipulator and a 4-bar mechanism, and I showed you how we can get the forward dynamics, how we can simulate the equations of motion of these two examples. The dynamics can also be done by software packages such as Adams. Okay, so in Adams, we can also simulate the mechanism of the manipulator, which is input to Adams. Okay, so with this, we will stop this lecture, which dealt with inverse dynamics and simulation of equations of motion. In the next lecture, we will look at a more abstract way of finding the equations of motion efficiently. Okay, this is called as the recursive formulation of dynamics of manipulators.